What you're seeing isn't a video game or CGI movie scene, it's Apple Maps. The photorealistic 3D rendering of entire cities with millimeter precision represents one of the most significant advancements in digital cartography. And while it's nice to look at, the even more stunning part of it was that this was supposed to be a missile guidance system produced by Swedish defense contractor Saab AB, at the heart of which was the concept of correlated velocity, a vector required by the missile at the specified position and time to achieve the position of the target for a given value of the total flight time, or in simpler terms, the exact velocity vector needed for a missile to hit its target under the influence of gravity and other forces. The Q guidance method used in these systems relies on a ton of math, involving the missile's actual velocity, its correlated velocity, and what engineers called velocity to be gained, all to make sure the missile hit exactly where it needed to be. Except Apple realized something in 2011. These same mathematical principles that guide missiles to targets could become the foundation for creating accurate 3D maps. The ability to precisely calculate positions in three-dimensional space, accounting for multiple variables and perspectives, translates perfectly to photogrammetric mapping. Under the codename Sputnik, Apple bought C3 and the team continued development in Sweden, now repurposing their military expertise for civilian use. The missile guidance algorithms that once calculated intercept trajectories was adapted to process overlapping aerial images, extracting precise 3D coordinates from 2D photographs, and the beginning of one of the greatest feats of photogrammetry available to civilian use began. But what is photogrammetry? Photogrammetry is the science and technology of obtaining reliable information about physical objects and the environment through the process of recording, measuring, and interpreting photographic images. While the term was coined by German architect Albrecht Meydenbauer in 1867, the technology has evolved dramatically since its inception. Apple's aerial data collection begins with specifically equipped aircraft flying at approximately 1,600 feet above cities. These aircraft carry an array of professional-grade DSLR cameras, at least 4 main cameras positioned at precise angles along compass points to capture buildings from multiple sides. Additional cameras, the exact number remains proprietary, capture overlapping images from carefully calculated perspectives, ensuring complete coverage of the urban landscape. This systemic image acquisition creates what photogrammetrists call stereoimagery, overlapping photographs that enable depth perception similar to human binocular vision. The flight planning is meticulously calculated to ensure optimal overlap between images, typically 60 to 80% forward overlap and 30 to 40% side overlap, creating redundancy that improves accuracy and eliminates gaps in coverage. In the back end, the computational process begins with stereoscopic depth calculation. As one search result explains, stereophotogrammetry involves the estimation of 3D coordinates of points on an object by considering measurements made of 2 or more images taken from different positions. The system identifies distinct visual features in multiple images and it triangulates their precise positions in three-dimensional space. This triangulation process generates millions of 3D coordinates through bundle adjustment processing, a sophisticated mathematical technique that simultaneously refines camera positions, orientations, and 3D point coordinates to minimize measurement errors. Camera calibration corrects for lens distortion and other optical aberrations, ensuring geometric accuracy. The result is a dense point cloud, a three-dimensional set of points representing matched features. This point cloud undergoes meshing to create a continuous surface model and texturing to apply photorealistic appearance. The final outputs include digital surface models, or DSMs, representing buildings and terrain, and orthophotos, geometrically corrected images that eliminate distortions caused by camera angles and terrain variations. Speaking of, thanks so much for all the support on the channel lately. It really means a lot, and I want to give something back to you guys. So do you need a job? That sounded a bit weird. But whether you're a UX designer, app developer, freelancer, or just a curious viewer, I want to get to know you guys, share some UX and UI tips, and maybe even get a gig. So I made a Discord channel for us and want to make this the place to be for front-end professionals. And I'm having talks with people to get some employers in there so you can connect with them too and find some jobs in the future. I'm really excited to get this thing started, so I hope you'll join me. Processing terabytes of data per city presents significant computational challenges, however, and Apple decided to automate it, exactly opposite to what Google Earth's early approach was, which relied on manual modeling using SketchUp to crowdsource 3D buildings. Apple's automated photogrammetry offers substantial advantages. It ensures consistency across vast areas, eliminating variability in crowdsourced models. It produces higher resolution textures, capturing building facades with pixel-perfect accuracy from multiple angles. Automated methods also create more accurate structural representations by precisely measuring building dimensions rather than approximating them. Perhaps most importantly, automated photogrammetry offers unprecedented scalability. While manual modeling required years to cover even major cities, Apple's system can process entire urban areas in a fraction of the time. This efficiency enabled Apple to implement 3D building support for approximately 26 cities by 2012, while Google Earth supported only 13 cities at that time. But these advantages come with substantial computational requirements. The process demands powerful server infrastructure for processing terabytes of raw imagery, significant bandwidth for delivery to devices, and sophisticated on-device rendering capabilities to display these complex models smoothly. Initial processing uses automated quality control to filter problematic images, identifying issues like motion blur or atmospheric distortion. The system selects optimal image sets and applies color correction for consistent appearance across varying lighting conditions. The 3D reconstruction pipeline employs two approaches. Structure from motion, or SFM, algorithms recover camera positions and sparse 3D points by analyzing feature correspondences across images. This feeds into multi-view stereo, or MVS, processing, generating a dense point cloud by computing depth maps from multiple views. The point cloud is then meshed and textured for photorealistic appearance. Before delivery, models are optimized using level of detail, or LOD, hierarchies, progressive loading techniques, texture compression, and geometry simplification. These methods preserve visual quality while reducing data size for efficient mobile rendering. This pipeline transforms raw aerial imagery into navigable 3D cityscapes, but the process isn't without significant technical hurdles. Creating photorealistic 3D city models presents several complex technical challenges. One significant issue involves temporal inconsistencies, when aircraft capture images of buildings from different sides hours apart, resulting in lighting discrepancies across a single structure. This is in addition to the weather, lighting, people, vehicles, seasons, or just being able to see parts of the building. To address these challenges, Apple employs temporal filtering algorithms that detect and reconcile time-based inconsistencies, and compositing methods to get rid of any seasonal or weather-related variation. Object recognition systems identify and remove transient elements like vehicles and pedestrians, and lighting normalization techniques compensate for different illumination conditions, while multiple pass photogrammetry fills occlusion gaps by combining data from various angles. Apple's approach to landmark modeling goes beyond standard building reconstruction. Significant structures receive higher resolution capture processes to preserve distinctive features. The workflow combines ultra-detailed photogrammetry with manual refinement by artists, resulting in accurate and visually appealing representations of iconic structures. Apple's 3D rendering engine, leveraging Metal API for hardware acceleration, efficiently processes complex data while maintaining smooth performance across devices. Key optimization techniques include frustum culling, rendering only visual objects, occlusion culling, skipping hidden objects, geometry instancing, reducing identical elements without duplicating memory, and texture streaming, progressively loading higher resolution textures. These methods balance visual quality with performance, delivering photorealistic city models to users' devices. The day-night transition system employs a dynamic lighting model that simulates natural illumination changes throughout the day. Rather than simply dimming the scene, the engine uses texture substitution techniques to display nighttime versions of buildings with illuminated windows and architectural lighting. Atmospheric scattering simulation creates realistic sky colors and distance fog effects that change with viewing angle and time of day. Performance benchmarks show the engine maintains consistent frame rates across devices through adaptive quality settings, automatically adjusting detail levels based on the device's capabilities. A technical achievement that transforms the massive datasets of photogrammetric models into an accessible, interactive experience that helps users understand and navigate complex urban environments in entirely new ways. And if you liked this video, why not see how Apple Maps' biggest competitor does it?